how do we calculate the equilibrium constant? We've done all this, writing the equations and stuff. Well, the most obvious, most direct way is to just measure the concentrations of everything at equilibrium and stick those numbers into the equation, right? Easy enough. So here's an equation. Suppose that H2 concentration is 0.11 molar, I2 is 0.11 molar, and the HI is 0.78 molar at equilibrium at this temperature. Calculate Kc. Okay, that doesn't sound too bad. So Kc equals, let's write the expression first. So it's going to be Hi squared, because there's a 2, divided by the H2 and the I2. Now we can plug the numbers in. So Hi was 0.78, and that's squared. And then H is 0.11, and I2 is 0.11. It's always a good idea to have your calculator out and do these calculations with me, because it's so much fun to catch me making a mistake, and I do make them a lot. So I'm coming up with 50. Anybody else get 50? Thanks. The other thing is you want to make sure that you and your calculator are on the same page and you're understanding what you're doing. Because this is a type of calculation where people do funny things. They do 0.78 squared divided by 0.1 times 0.1. Your calculator doesn't understand that and will give you a completely different number. So if you're not coming up with the right answers, come and see me. I am the calculator whisperer, and I can get your calculator to shape up. Because it's not your fault, it's your calculator's fault, right? You just have to, first you start out being real nice to them, and if they don't respond to that, that's when you get mean. But I promise I will not throw your calculator on the floor like I did to mine the other day. So let's look at this table. Wow, there's a whole bunch of numbers. This is the same equation we were just looking at. And here are initial concentrations and equilibrium concentrations. So they did several experiments. What is that? 5 experiments, starting with different starting amounts. Here they've got just reactants, no product. Here, no reactants, only product, equal amounts, and twice of one compared to the other. And then measuring the equilibrium concentrations. You plug them into the equilibrium expression, and what do you get? The same number, because it's an equilibrium constant, right? No matter what concentrations you start with, you're going to end up with that relationship that gives the same constant for the equilibrium. So the equilibrium constant is the same regardless of the initial concentrations. At a particular temperature. You change the temperature, all bets are off. Things are going to be different. But keep the temperature the same. You can start with anything you want, and you'll end up with the same.
The reaction itself, is exothermic, and it would change the temperature itself.
Yeah, if the reaction involves energy, if it's exothermic or endothermic, then altering the temperature can cause even larger changes than you would expect in just one that doesn't depend on things like that. Temperature affects all kinds of things.
Do you ever get reactions that don't come to a stable equilibrium, but it's keep bouncing back and forth between a midpoint?
Not that I know of. If the conditions around them are constant, it should come to a constant equilibrium. It's dynamic, it's going back and forth, but those rates will equal out. Well, maybe let's go back here just a minute. So that's a great way to calculate an equilibrium constant. What's difficult about doing it that way, though? Here you've got this mixture of gases. How do you find the concentration of the hydrogen and the iodine and the hydrogen iodide? How do you measure those without disturbing the equilibrium? That's the problem, is it can be hard to measure all of them. So it turns out we can also calculate the equilibrium constant if we know the starting concentrations of the reactants and we know the equilibrium concentration of just one of the reactants or the products, just one species. And so that makes things much easier. Like we did with the bleach, we were looking at that dye. It had a color, and we could measure the concentration using absorbance. And that's what we're going to do in lab tonight, is we're going to look at a different colored compound and measure concentration using absorbance. You can't do that for compounds that don't absorb light. It just doesn't work. And if you've got multiple compounds that absorb, then things get complicated too. So this is where we get into the ice tables. So here's an example, very simple reaction. A forms 2 molecules of B. 1 mole of A forms 2 moles of B, and this is going to be in some sort of an equilibrium. And we know that the initial concentration of A was 1 molar, and the initial concentration of B was 0. We started out with all reactant, no product. Then we measure things at equilibrium, and we find that the equilibrium concentration of A is 0.75. We can fill in the rest of this table using stoichiometry. And this is what that question on the worksheet, the math review worksheet, was kind of introducing you to, is how to think about this. So if this started at 1 and it went to 0.75, what was the change? It went down by 0.25, right? So the change is minus 0.25. If 0.25 of A reacts, how much B does that make? Twice as much, right? So if that's minus 0.25, this must be 0.50. This is saying that 0.25 moles per liter of A reacted, and that would generate 0.25. So if it started with 0 and the change was 0.5, then the equilibrium concentration is 0.5. And we figured that out by only measuring one of them. Now what's the equilibrium constant? Kc equals B squared over A, right? Always write that out first, and then put the numbers in. So we've got 0.5 squared divided by 0.75. So Kc equals 0.33, or 1/3 if you like fractions. Any questions? The beauty is you could start with lots of different initial concentrations. It's going to go to equilibrium and be the same constant. And so as long as you can measure one, you can figure out the equilibrium concentrations of everything else. Oh, another thing I should have just pointed out. We call these ice tables. Initial, change, equilibrium. Initial, change, equilibrium, ice. I don't know about you, but I could use some ice right now because it is warm in here. So the reaction shown between carbon monoxide and hydrogen carried out with initial concentrations shown there at equilibrium. It gives you a concentration. Find the equilibrium constant. Well, I often like to just use the equation as the basis, as the labels for my ice table. So here I've got I, C, E. So initial concentration of carbon monoxide 0.27, of hydrogen 0.49. Now, it doesn't say anything about the initial concentration of the CH3OH, that's methanol. If it doesn't say anything and it's a product, probably there was none there to start with. You put the two reactants in and you see what's going to happen. It's actually fairly unusual to put a mixture of everything, all the products and all the reactants, and have measured all of that and stick it in. Because it's much easier to have some of them be 0. So this is 0. And then we've got the methanol concentration at equilibrium is 0.11. So now we're going to fill the rest of it in. So the change in the methanol, it went from 0 to 0.11. That's a change of plus 0.11, right? So the reactant went up. That means that the product concentrations have to go down because they're being used up. That's what's making the product. So if this went up 0.11, how did the CO change? It went down 0.11. Because our balanced chemical equation here says 1 mole of this makes 1 mole of that. The volume isn't changing. So that went down by 0.11. Here, this is 2H2. It takes 2 of these to make 1 of those. So am I going to multiply 0.1 by 2, or am I going to divide by 2? I'm going to multiply. So this is going to go down by 0.22. Because it takes 2 of these to make 1 of those. So this is going to be 0.16, and this is going to be 0.27. Now I have my equilibrium concentrations. Kc equals CH3OH over CO and H2 squared. Now I put my numbers in, 0.11 over 0.16 and 0.27 squared. 0.11 divided by 0.16 divided by 0.27 squared equals 9.4. Any questions? Does that reaction favor reactants or products? It's pretty close to 1, isn't it? 9.4. So it favors the products a little bit. And when we look at the equilibrium concentrations, we see that even though we started out with high concentrations of these, the reaction did go in the forward direction. And now we have significant concentrations of everything.